Very good morning, my dear friends. I welcome you all to my YouTube channel. And friends, in today's video, we are going to work out a problem on a curved beam, that is a crane hook having trapezoidal cross section. And friends, you remember this is one of the most important type of questions asked in the examination, and also this is the most preferred choice of many examiners. Friends, here in the present video, friends, we are going to have a crane hook used to lift a load of 90 kilonewton, and we have been asked to find out what are the values of RC and Rn, and what are the normal stresses due to bending at the inner and outer fiber, the value of maximum tensile stress and also shear stress. You've also been asked to plot the variation of stress across the critical cross section. Friends, here you can see this crane hook which is used to lift a load of 90 kilonewton as specified in the problem. And you will have to find out what is RC and Rn. So, to calculate this RC, we have to just write down the cross section, mark the center of curvature, and RC is the distance of the centroidal axis. You say to find RC, comma Rn. RC is the distance of the centroidal axis from the center of curvature C. So friend, this distance is called RC. So I have split this into two parts. RC is equal to Ri plus x bar. X bar is the distance of CG of this from the inner fiber B. So friends, for this RC, I'll write down here. RC is equal to Ri plus x bar. Ri is the inner fiber distance that is given here as 65 mm. So 65 plus x bar. Friend, what is this x bar? If you see this cross section, friends, this is symmetrical about this horizontal axis, and CG lies somewhere closer to the inner fiber. This is our x bar. Friend, this x bar for the trapezoidal section is given by the formula h by 3 bi plus twice b naught divided by bi plus b naught. Friend, this is the formula available in machine design data handbooks. You have this formula. Then what are these bi, b naught, h, etc.? Friends, the maximum inside width, this is bi, and the outer dimension of the cross section is b naught, and these two are parallel to each other. And here h is this distance, the height or the width of this cross section. So friends, as per the diagram, h is 116 mm divided by 3, h by 3 bracket bi, the inside maximum dimension of the trapezium, that is 90, plus 2 times b naught. B naught is this dimension, that is 25, is that b naught, divided by bi plus b naught. Bi is 90, b naught is 25. Friends, if you simplify, the value of x bar works out to 47.07. 47.07 mm. So friends, if you want this this RC will be RI, that is 65 plus x bar is 47.07. This will be 112. The value works out to 112.07. 112.07 is the value of RC. That is, the centroidal axis of the trapezoidal cross section is at a distance of 112.07 not 7. It's asking you what is Rn. Friends, Rn stands for the distance of the neutral axis from the center of curvature C. So friends, this I have marked in the diagram little closer to this G towards the inner. This is our Rn. So Rn, I told you in previous videos that the values of Rn in terms of the dimensions of that cross section are given in the machine design data handbook. And for a trapezoidal section, I will say for trapezoidal cross section, the Rn is given by the formula Rn is equal to h by 2 bi plus b naught divided by bi r naught minus b naught ri divided by h ln of r naught by ri minus bi minus b naught. This is the expression for the Rn of the trapezoidal cross section. Friends, here you know all the values. H is equal to 116 mm given, bi is equal to 90 mm, the maximum dimension of the trapezoidal section, b naught is 25 mm, and friends, this Ra is 65 millimeter from the center of curvature to the inner fiber. This is our Ri, that is 65 mm, and R naught. Friends, R naught is the distance of the outer fiber A from the center of curvature. So this is Ri plus this value H. This is Ri plus H. That is Ri is 65 plus H is 116. This R naught works out to a value to calculate here. That is 181 millimeter is the value of this R naught. Friends, if you make this substitution in the formula, you will get this value of Rn as Rn equal to 103.4583, 103.4583 millimeter. Friend, you have Rn, you have Rc. The moment you have these two, you will be able to calculate some of the parameters connected with this, such as E. E is equal to Rc minus Rn. So this value E works out to 8.6117. Then we have got Ci is Rn minus Ri. What is the distance here is? This is Rn, this is Ri. The difference between those two is Ci. So friends, this is 103.4583 minus 65 is Ri. That Ci works out to 38.4583. 38.4583 millimeter. And friends, there is another important term, that is C naught. I told you in one of my previous videos on this chapter that C naught is equal to H minus Ci in case of rectangular section, trapezoidal section, etc. If it is a circular section, it is going to be D in place of H. So this H is 116 minus Ci value 38.4583, and this works out to 77.5417. 77.5417 mm. So you got Ci, C naught, all the values you have got, friends. Now let us go to the second part of the question. In the second part of the question, we have been asked to determine normal stress due to bending at the extreme fibers. The notation used for the normal stress due to bending at the extreme fibers, that is A and B. A is the outer fiber, B is the inner fiber. So to find sigma Bi comma sigma B naught. So these are the normal stresses due to bending at the inner and outer fiber. Friends, sigma Bi is given by the formula MBCI divided by AERI. The formula is available in the machine design handbook. What is this MB, friends? This MB stands for the product of P into RC. We know P, it is 90 kilonewton. I am going to convert that to Newton by multiplying by 10 to the power of 3, and the value of this RC is 113.07. 113.07. So you will get the value of this MB. CI we have calculated, RI is 65, E we know, and this A stands for the area of cross section of this trapezoidal section, that is given by the formula H by 2 Bi plus B naught. That is half the height into sum of the parallel sides. That is H by 2 116 by 2 multiplied by Bi is 90, B naught is 25. Friends, you get this area of cross section. So you will be able to find out what the area is. So friends, once you substitute this value, you will get the sigma Bi, that is at B, the inner fiber. I can say at B. You get this value of sigma Bi, and this sigma Bi works out to 103.89. 103.89. Sigma Bi is equal to 103.8918 Newton per mm square. This is the value of the normal stress due to bending at the inner fiber B of the critical section AB. Friends, on the same line, you can find out what is normal stress due to bending at the outer fiber. I can say at outer fiber, that is at A. A is the outer fiber. You can see here at A is given by sigma B naught is equal to minus MB C naught divided by AE R naught. Friends, you know all these values. Substitute them and you will get this value of sigma B naught as minus 75.2257. Minus 75.2257 is the value of this normal stress due to bending at the outer fiber, that is at A, is so much. So we have found out what is the value of normal stress due to bending at the inner fiber, that is at B, and also at the outer fiber. Friends, in the third part of the question, we have been asked to find out what is the maximum tensile stress and its location. Friend, this is a very important point. That is, for all the crane hooks, irrespective of the cross-sectional area or the cross-section, the maximum stress, which is tensile in nature, that is to say, the maximum tensile stress occurs at the inner fiber, that is at B, because this gets elongated when the load is being lifted by the crane hook. So we will write down this as sigma max, maximum tensile stress, that is sigma tensile maximum, is nothing but sigma I total stress at B, the inner fiber, that is given by sigma D plus sigma Bi. So this is always the case. Whatever may be the cross section of the crane hook or the curved beam, when it is lifting a load, the maximum tensile stress occurs at the inner fiber, that is at B. This is a very important concept and you should remember. Friends, this I will substitute. Sigma D is load over area of cross section plus sigma Bi is MBCI divided by AERI. Friends, we know all these values. Load is 90 kilonewton. Convert that to Newton. Area is pi by 4 d square. That is, it is not pi by 4. Area already we have calculated as half the height into sum of the parallel sides. That is h by 2 bracket 90 plus 25 area Bi plus B naught plus MB value have calculated, Ci we have calculated, again area is the same, E we have calculated, Ri is 65. If you make the substitution in this formula, you get the maximum stress as 117.39. 117.39 Newton per mm square. Friends, this is a tensile stress and this tensile stress occurs at the inner fiber, that is at B of the critical section AB. That is location they are asking, that is at the inner fiber, you should write. Friends, finally, we have been asked to find out what is the maximum shear stress and where does it occur, or what is the location of the maximum shear stress. Friends, in one of the previous videos on these curved beams, I told you the maximum shear stress is half the maximum tensile stress. So tau maximum shear stress is sigma tensile by 2. So that is equal to sigma tensile stress at the inner fiber 117.39 divided by 2. So that works out to 58.695 Newton per mm square. This is the value of the maximum shear stress and its location. The maximum shear stress occurs at the point where the maximum tensile stress occurs. That is, this value of maximum shear stress occurs at B, that is the inner fiber of the critical cross section. Friends, finally, we have been asked to plot the variation of the stress across the critical cross section. So variation of stress is to be plotted. So we know all the values. We have calculated the values of all the stresses, the direct stress and the normal stress due to bending, and we can plot this variation. So for this, we'll say here plot of stress variation across critical section, that is AB. Friends, you will draw two lines indicating H, the width of the cross section, and here friends you will write a line indicating the normal, that is the neutral axis, center of curvature here. I can see here this is the neutral axis. If it is a circular cross section, you have to have D here. So friends, I will just mark a line here and mark the outer fiber as A, the inner fiber as B, and here we are going to plot, to start with, what is called direct stress. Direct stress is sigma D, that is equal to sigma D, that is equal to P by A. Friends, this direct stress value can be obtained from this formula. That is, you know the load 90 into 10 to the power of 3 Newton area h by 2 116 by 2 into the sum of the parallel sides 90 plus 25. Friends, you get this value. This is tensile in nature. So direct stress in case of all curved beams, that is the crane hook particularly, are tensile in nature. So friends, you get a value and you can just write a line here indicating what is this sigma d. Sigma d is the maximum stress, that is the tensile stress. So I will just write down a box, a rectangle with height is equal to the value of sigma d you get from here, and this is written to some scale. It will have the same magnitude across the critical section AB. So here also it is sigma d. Friends, next we will plot the sigma bi and sigma b naught, that is normal stress due to bending at the inner and outer fiber. At the inner fiber it is sigma bi, at the outer fiber it is sigma b naught. Inner fiber is B, outer fiber is A. Friends, this sigma bi is given by the formula MBCI divided by AERI. You know all the values. Say you get a height like this, and sigma B naught is equal to minus MBC naught divided by AE R naught. Remember friends, when the normal stress due to bending at the inner fiber is positive, it is going to be negative here in all curved beams. If it is positive here, it is going to be the other way, negative. Friends, so here I am going to plot some value, the value whatever you get here, and join these two by a curve like this, and we will say here, this is how the stress varies from A to the neutral axis, that is going to be negative, and this height will give you the sigma bi, so which is positive. Finally friends, we have to plot the resultant stress or extreme fiber stress. So here it's at B, it is going to be sigma direct plus sigma bi. In other words, it is a summation of this height plus this height. So both are positive, and hence I am going to mark a height here which is the summation of this height plus this height. So it is going to be something like this is our sigma I, the resultant stress on the inner fiber. Similarly friends, here this is negative, this is positive, the difference will be the resultant stress at the outer fiber A. Friends, and this value is going to be sigma d minus mbc naught by AER naught. The magnitude you have to plot here. And again friends, draw a curve passing through this neutral axis. Show the direction of the compressive stress. The arrow should touch the reference line like what I have done here. This is the outer fiber, and the inner fiber is going to be tensile, and this height, the magnitude is the sum of this plus this. Direct stress plus bending stress is this total height as resultant stress or the total tensile stress, and here this height is equal to difference of these two, because one is positive, other is negative, you get a value, negative value here. Friends, this is how the direct stress, the normal stress due to bending, and the resultant stress appears across the critical cross section AB of the beam. Friends, I hope the presentation was interesting, and if you like this video, do share with all your friends without fail. Thank you very much for watching my YouTube video.